Next, we'll look at separate chaining, a collision resolution strategy that makes use of elementary linked lists. So what are we supposed to do when two different keys hash to the same index? The birthday problem tells us that we're going to have collisions. You need a quadratic amount of memory to avoid collisions. And the load balancing and coupon collector analysis tell us that the collisions are going to be evenly distributed among the table, around the table. So what we want to do is have an easy way to deal with collisions. And so the first way we'll look at is called separate chaining, and it's a very old idea going back to 1953. And the idea is just build a linked list for each of the table positions. So we'll have a table that's smaller than the number of keys that we have. The hash function will map each key to some integer. So in this case, we have a table of size 5. So the hash function will map any key. In this case, we'll use single letter keys. It'll map any key to an integer between 0 and 4. And then to do an insertion, we'll just keep a linked list at the table position corresponding to the hash value. So S hashes to position 2. It'll be on the linked list that first link is at position 2. And then E goes to 0 and A goes to 0. And for search, we're going to have to go to, if we're going to look at is C in this table, say, we're going to find the hash value for C, and we'll look down the list to see if we can find C. So we have to look through the whole list for search, but you only have to look through one list out of all the lists. Essentially, if you have M entries in the hash table and n keys, the length of the list you're going to have to look at is about n over m because they're evenly distributed. So that's a straightforward and simple scheme for implementing symbol tables with hashing. Now we could use a iterable bag or some data structure like that and hide the linked list structure underneath, and that's a perfectly fine way to proceed in modern programming. This implementation directly implements the linked lists. Now, for a practical situation, we pick some value of m. You could make it so that the hash table itself grows once it gets really huge, and such hybrid methods are easy to implement, so we won't talk too much about that. We need to, just in terms of implementation details, our keys and values have to be objects because we can't have an array of generics. Since we're making an array of nodes, and node would have generics if we're used to key and value, so we have to make them objects, and then when we get things off, we're going to have to cast. This is the get procedure. So to look for a key in the hash table, we compute a hash value, and our hash function is pull out the system hash code, make it positive by ANDing off the sign bit, and then mod with m to get a number between 0 and m minus 1. So we pick that number I, and then we just go to that list, and this is the standard code for traversing a linked list. Start at the first node, as long as it's not null, go x equals x dot next, and if you find a key that's equal to the key you're looking for, return the value, and we have to cast it to value because of the generic array creation problem in Java. Otherwise you return null. So that's not much code, and it's trivial code at that for doing an efficient symbol table search using hashing. And insertion is not much more difficult. If you do the same thing, and if you find a node with key equal to the key on the linked list, you reset the value and return. Otherwise, you make a new node and put it at the beginning of the linked list with this standard code. Replace st of I with a new node that links to the old st of I. So again, very little code to implement search and insert using hashing, and that's why it's so popular. And what about the analysis? Again, the standard probabilistic analysis of the balls and bins problem tells us a lot of information of what goes on. And again, if the uniform hashing assumption holds, the probability that the number of keys within a list is within a constant factor of n over m is extremely close to 1. So it means that we've divided the search cost, which would be n if we have a sequential search, by a factor of m. And in many applications, even setting m equals to 100 or 1,000 is going to be very effective, and that's why so many systems programmers use that. So number of probes for search and insert is proportional to n over m. Now, typically what a programmer would do is try to figure on making m about equal to the number of keys divided by 5, say. So if you can't make m too large, you have too much space, and you'll have empty chains or short chains. And if you make m too small, then they're too long, you have to search through them all. So let's say n over 5, and then you get constant time searches and not much extra space. You have extra space for the links to implement the linked list, but the rest of the table is not much extra space. And those are typical parameters. If you want a full service symbol table, which is going to grow from small to huge and then back down to small again, then you'd want to use array resizing to make sure that m is always within a constant factor of n. But we'll leave that detail out for now. So that brings us to this summary. Where red-black trees, we were happy with log base 2 of n for search and insert. With separate chaining, you can really get it down to a constant number of operations for search and insert. So hashing's going to be preferred for short keys where the hash function is easy to compute and where we don't need ordered iteration or any of the ordered symbol table operations, because it has really fast access to the symbol table. That's our first collision resolution method, hashing with separate chaining.